define rational functions, and with that we're going to look at the domain and how to find something called the vertical asymptotes of a rational function. And so first of all, what is a rational function? It's a function here we call f of x that's defined as p of x over q of x, and p of x and q of x are both polynomials. Okay, so for example, we might have something like f of x to be x plus 1 over x to the fourth minus 1. That's an example of a rational function. There are two key elements to a rational function that you need to go over when you're first introduced to this concept. The first one is domain. The second one is vertical asymptotes. So I'm going to try to show both of those. But we need to recall what we mean by domain. So if you remember, a good way to think of a function is taking two sets, and the function picks an element out of one set and maps it over to the other set, like that. And so commonly we'll pick an x, put it into f, and end up with a y. Now, the first set that we pull from is what we call our domain. This is the set of numbers that we're allowed to choose something from and get an answer. So think about a vending machine. The set of x's are the American coins that you can put in the vending machine to buy your chips. If you try to put in a Canadian coin, it breaks the machine. The Canadian coin is outside the domain of what we're allowed to put in the machine. Okay, so the way to think about this is you think about the things that you're not allowed to plug in. So if you look at our function here, f of x, we have p of x over q of x. The polynomials have domains negative infinity, positive infinity, but for a rational function, what we need to make sure is that our denominator is not 0. Okay, so we can say then the domain of a rational function, f of x being p of x over q of x, is all x such that our denominator, q of x, is not 0. Alright, so that's it. To find the domain, all you need to do is make sure the denominator is not 0. Okay, and I'm going to go over a couple examples, and I want to look at the graphs because we can figure out something about the domain, and the second topic, which is vertical asymptotes. Alright, so let's look at example 1. Okay, so here's my function, f of x equals 1 over x minus 1. This is rational, and we can quickly see here that my domain is anything that doesn't make the denominator 0, and the denominator is 0 when x minus 1 is 0, so my domain is x, it can't be 1. X is not equal to 1. Now I can write that as a set. If you prefer interval notation, you can write it like this, negative infinity to 1 and 1 to infinity, which is basically the number line. You take 1, cut it out. Anywhere else is okay, but 1 itself is not. Alright, you might want to write it in set builder notation, which you could write like this, x where x is not 1. So depending on your textbook, you might want to use one of these three different options. So this is the graph of f of x. We have these two pieces here that kind of bend up like that. And right at 1, you have this straight line that it doesn't cross. It creates like a boundary between these two pieces. And this straight line is what we call a vertical asymptote. And to define a vertical asymptote, it's simply a vertical line that your graph cannot touch. Okay, so if you notice here, we said our domain was anything but 1. Okay, and if you look at my graph, I could pick any x value along here and find a function value, right? So I'm allowed to pick any x I want and plug it in and get an answer on my function, except for the value 1. If I plug the value 1, I'll never hit a function value there, right? So the asymptote is a visualization of the fact that my function doesn't have 1 in its domain, but everything else is included. Okay, so that would lead me to believe then that maybe the way to find the vertical asymptotes is simply letting the denominator, in this case x minus 1, be 0, okay, and then I found the equation of my asymptote, which was x equals 1, the very thing that I couldn't have. Okay, now you are mostly correct in thinking that, so let me show you another example that will have this plus one caveat, and I think we'll get the full picture. Okay, so this time we have g of x to be x minus 2 over x minus 2 times x minus 1. Alright, so if I'm thinking about the domain, again, I'm thinking about how do I get that? I set the denominator equal to 0, and those are the things I can't have. So if I took this guy and said, okay, that can't be 0, then that means x can't be 2 and it can't be 1. So my domain is anything but 2 and 1. Alright, so if you want to write that in interval notation, you can say negative infinity to 1, and then 1 to 2, and then 2 to infinity. Okay, that means you take your number line, you cut out 1, and you cut out 2. But anything else works, just those points will not. Okay, so that's my domain. What about my graph? Well, let me show you. Okay, so here's my graph. Now notice, this looks very similar to the graph I had last time. I have a vertical asymptote here at 1, and that has equation x equals 1 is the vertical asymptote. According to my domain, 2 shouldn't be in the graph. Okay, so maybe there should be an asymptote at 2. Well, actually there's not. So if you notice here, from my original, I could have canceled out the x minus 2, and when I did that, I'd get 1 over x minus 1, which is the function we had in the previous example. Okay, so this thing looks exactly like the function we just had, except I multiplied in x minus 2 over x minus 2. Doing that does not create an asymptote. It creates this. It creates a hole in the graph. Alright, so this graph looks the same as f of x equals 1 over x minus 1, except since I multiplied in x minus 2 over x minus 2, I got a hole in the graph. Okay, so what does that mean then? To find vertical asymptotes, you need to set the denominator equal to 0, but before that, you need to factor out common factors from the numerator and denominator. So to find vertical asymptotes, what do? First, we factor the denominator and the numerator and cancel common terms. Secondly, set the denominator equal to 0. The solutions from that equation are the equations of your vertical asymptotes. Now, I want to keep in mind though, the domain still includes the stuff that got canceled out. Alright, so let's look at 3 examples, and we can do them really quickly and find the vertical asymptotes. Okay, so here I'm trying to find the domain equations of vertical asymptotes of these 3 functions. Let's start with A. Okay, so first let's find our domain, because all I have to do in that case is set the denominator not equal to 0, so my domain is anything but negative 5. For vertical asymptote, I need to first cancel out the common terms of the numerator and the denominator. In this case, the numerator doesn't factor, and neither does the denominator, so the one element that wasn't in my domain actually creates a vertical asymptote. Okay, so there's the equation of my vertical asymptote. The domain is x is not equal to negative 5. The vertical asymptote is x equals negative 5. Alright, let's try B part. My domain, again, is I'm going to take x squared minus 1 and set it not equal to 0. Now that does factor, so then I get x is not equal to positive 1 and negative 1. Okay, those are things not in my domain. But now notice here, if I did a little bit of work, I could factor g of x in the denominator, again, as x plus 1, x minus 1. And now notice that I have some stuff that cancels out. So since that stuff canceled out, that does not relate to my vertical asymptote. So my vertical asymptote is just what's left over set to 0. So my vertical asymptote is at x equals negative 1. Now compare, I have the domain is anything but 1 and negative 1. But my asymptote's just at negative 1, which tells me that at 1 here, what happens? There's just a hole in the graph. Okay? Or let's look at part C. So again, the domain, I can't let x squared minus 1 equal 0. So that factors just like we did. We get x is not equal to 1 and negative 1, just like last time. Okay, now what about vertical asymptotes? Well, this time, there's nothing in the numerator that'll cancel out with the denominator. So my vertical asymptote still will come from x plus 1 times x minus 1 equal to 0, or x equals 1 and negative 1. In this graph, you do have 2 vertical asymptotes at 1 and negative 1, and that matches exactly with your domain. Okay, I hope this makes sense. The only thing you really have to worry about is to cancel out the common terms from the numerator and the denominator. Those are not vertical asymptotes, they're holes. But everything else will be a vertical asymptote coming from your denominator. I hope this makes sense. Try to relate it to the picture. I think that helps clarify things. If you have any questions, I'll be glad to help. And thank you for watching.